Okay, so this is exam 1. The first is I have this configuration of particles. I want you to tell me what is the um, sketch the E-field vectors. So this is my coordinate system right here. Let's go to a different color, and then my vector for charge 1 is going to be in this direction, so I'll call that E1, and then E2 is going to be an attractive force on that test particle, so my E2 is in that direction. Let's go ahead and figure out what is this angle. I'll call it theta. Notice that this is a 3, 4, 5 triangle. And I want to know what is this angle theta, and so that theta is the inverse tan of opposite over adjacent, so it's 3 over 4, so that's equal to 37 degrees. So that angle is 37 degrees right there. And then I need to calculate E1 and E2, the magnitude of those vectors. That's going to be KQ1 over R1 squared. That's 9 times 10 to the 9th. Q1 is 32 times 10 to the minus 9 divided by the distance from here to here. This is R1, and that is 4 squared. 4 squared is 16, so that cancels with that. That cancels, and that leaves me with 18 newtons per coulomb. And then E2 is similar. I'm not going to write the equation, but I'll write out the numbers here. So that's 25 times 10 to the minus 9 divided by the distance, which is 5 meters squared. That's the distance from here all the way over to here. It's that side of the triangle. The square root of 3 squared plus 4 squared is equal to 5, but that's that special 3, 4, 5 triangle. And that leaves me with 9 newtons per coulomb. So now I'm left with, let's see, so that is part A. Now for part B, this is actually part of part B, is figuring out what those vectors are. But now continuing on with part B, we need to write out what are the x and y components. I'm going to redraw this, and I'm going to now label my x and y components. So E1 is 18, so it's just right here, 18 newtons per coulomb. But E2 is in this direction, and it has two components, here and here. So I'm just going to draw those two components that are in the negative x and negative y directions. And then let's go ahead and label this as E2y. That's going to be 9 times the sine of 37, and E2x. That's 9 cosine of 37. See, 9 of cosine of 37 is equal to 7.2. Keeping 2 sig figs, because I got 2 sig figs throughout here. And then 9 sine of 37 is 5.4. Okay, so now I need to find the magnitude. So moving on to part C, those are the x and y components of all those vectors. And now, all of these parts really just sort of run together, right? Because we're trying to find ultimately what is the magnitude and direction of the final electric field. So now I'm going to add up my x components. That is to say it's going to be 18 minus 7.2. What's that, 10.8, or I'll just call it 11 newtons per coulomb. And then I add up the sum of the y components, and that's just going to be 5.4. It's actually in the negative y direction. All right, so drawing these vectors now, let's go back to blue. I have 11 in this direction and 5.4 in this direction. So I know that my net vector, my net electric field, is going to be in this direction. I'll call this angle phi. If I want to know the magnitude of that, it's going to be the square root of 11 squared plus 5.4 squared. I get 12 newtons per coulomb. And then the angle phi is going to be the inverse tan of 5.4 over 11. That's opposite over adjacent. I get 26 degrees. So it's 26 degrees below the plus x. Of course, there are some other ways to say that. I could say negative 26 degrees from the plus x. The negative denotes the below. Or I could say 334 degrees from the plus x, and then that would be this angle, which is 334 degrees. Okay, let's see, I think we got most of that. Okay, actually, on part D, I'd intended for you to give this angle, but I'll also take this answer as well. And now finally for part E, this is part D right over here. For part E, I want to calculate the potential. So the potential is going to be V1 plus V2. Remember, these are scalar quantities, so that makes it really easy. Q1 was 32. It's positive, and then the distance there was 4 meters, plus 9 times 10 to the ninth. Be careful here, this is negative. Make sure you get that negative. It's important for our potentials, divided by 5 meters. Now I can do a bunch of cancellations there, 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 there. That goes to 5. This 4 makes that an 8, so that's 72 minus 45, which is what? 50, 22, 27 volts. This is 27 volts, so that's the answer there. Okay, sketch 5 to 6 electric field lines. It's important that we get the appropriate number of field lines, and a really great way to do this is, well, I know that the ratio of the field lines has to be 5 to 2. That means that the 5 coulomb charge should have 2.5 times more, because 5 divided by 2 equals 2.5, should have 2.5 times more lines than I do for the 2. But the really easy way to do this is just to say, well, I need 2 field lines coming out of the 2 coulomb charge. They're going to originate at that positive charge and terminate at that 5 coulomb, that negative charge. But then, because that 5 coulomb charge is bigger, I need 3 additional lines coming like that will go out to infinity. So there's my electric field lines, or something, similar to that. And now drawing my equal potential lines, they should always be perpendicular. So I'm looking that these angles are 90 degrees. So it's going to look something like this. Like that. I might have one that comes over here. Something like that. Okay? So those are my field lines and my equipotential lines. Proton moves from a potential of 8 volts to a place where the potential is negative 2 volts and moved a distance of 0.2 meters. The electric field in this region is constant. What is the speed of the proton? Well, let's just remember some basic ideas. That my potential is equal to an energy per charge. Potential is energy per charge. So I can say that the potential is equal to kinetic energy over a charge. My change in potential gives me a change in kinetic energy. Here, my change in potential is 10 volts. So that's going to be equal to my kinetic energy, 1/2 mv squared. It starts at rest, so it's going to have, that's going to be its final kinetic energy divided by the charge Q. A little point about delta V here. So I glossed over something. Delta V is equal to VF minus V initial. That would be negative 2 minus 8, which is equal to negative 10 volts. So my change in potential actually is negative 10 volts, but since I'm only looking for the speed, I don't need to worry about that negative sign, so I'm just going to sort of drop it off here. So my 10 volts is equal to 1/2 mv squared divided by Q. Look, I know all these values because this is a proton, and so the mass of the proton is 1.67 times 10 to the minus 27 kilograms, and the charge of a proton is 1.6 times 10 to the minus 19 coulombs. So I'm going to have 10 is equal to 1/2. Actually, let's see. I'm going to go ahead and just solve this for V. So I have V is equal to, that's the speed. Let's just, instead of putting in a number in here, let's just leave that as the voltage. So V then is equal to QV Q times V divided by 1/2 M, the square root of that. So I have 1.6 times 10 to the minus 19. I'm putting this in parentheses. I'm doing the square root of the whole thing. Times V, which is 10, divided by 0.5 times 1.67 times 10 to the minus 27. Square root it. I get 44,000 meters per second. All right, so that is the answer for that, that V is equal to 44,000. And then I know what is the electric field. Now there is an equation on your equation sheet that does this, but I just want to remind you that the units for electric field are not just newtons per coulomb, but they're also volts per meter. So I can just say then that the electric field is equal to a change in velocity over a change in x. And I get that from this. Now it's also on your equation sheet, and there's a reason for that, like a mathematical reason for that. But I can look at the units and understand that that's true too. So if I want to know the electric field for part B, the electric field is equal to delta V over delta x. That means that I can figure out the electric field, the magnitude of this vector, just by looking at what is the change in potential over a given region, and that's really useful. So my delta V is 10 volts. My delta X, I'm told, is 20 centimeters or 0.2 meters, and so that's 10 divided by 0.2 is 50 newtons per coulomb, or let's call it more particularly volts per meter. So that is the magnitude of the electric field. Okay? Let's do the multiple choice here. Consider this configuration of charges. The plus 2q charge is the distance d, and the and a distance 2d from the plus 4q charge, which best represents. So let's just first draw this vector. That is the vector from this charge. Now, this charge is twice as big. Let's write out Coulomb's law. KQQ over r squared. So I have a charge that is twice as big, so you would expect a bigger force, except the distance is also twice as big. So actually, my force is going to be half the size. That means that D is the right answer. Because look, I have a big vector, a small vector, the resultant is going to be there. If they were the same vectors, the resultant would be at 45 degrees. If the y component was bigger, it would be at that angle. But D is the right answer here. Consider these two charges, x is equidistant. Where can you place a charge where the net force on that charge is 0? So let's just start looking around, right? If I put a charge here, both forces are going to be in that direction. Likewise, if I put a charge here, both forces are in that direction. So to the left of plus q I can get rid of, and to the right of plus 2q I can get rid of, because I'm never going to get a 0 force from those two force vectors because they're in the same directions. Imagine if I put it right here, I get a really big force from the plus 2q charge, but I get a force that's half the size from the plus q charge, so it can't be at x. It has to be either D or E. And if you remember, I said you want to, in general, get far away from the bigger charges. So let's see how that works out. Due to the plus q charge, I get a force in that direction. Now I would get a force that's twice as big for the plus 2q, except I'm farther away. So I'm going to get a force that is possibly the same size. So that means it's in between plus q and x. So number 2 is D. What is the net force on Q2? All right, let's just think about this for a minute. Notice that this charge is 4 times as big, and the distance is twice that distance. So this charge is 8, which is 4 times 2. This distance is 4, which is 2 times 2. So back to my Coulomb's law, KQQ over r squared. If I quadruple the charge and double the distance, I'm going to get the same force. So what that tells me is that the force that's due to Q3, that's F3, is the same as the force that's due to Q1, that's F1. Okay, so to say all that to say that the answer is 0. Now you can go through and calculate these forces and you'll find that they're equal and opposite, but this is a much easier way to do it. Figure has 3 charges. The charge S experiences a force of 16 newtons due to charge Q, which is 4 meters away. Another charge is 2 meters away. It has twice the charge. What is the direction of the net force on S? So I know that this force is going to be in this direction. Okay, I know that because it says that this charge is the same sign as this charge, so it's going to also experience an attractive force. Get that out of the way. By the way, so that would get rid of this answer, just that answer. Okay, now I want to know what is the relative sizes of it. Again, let's write out Coulomb's law, KQQ over R squared. For this force, I have twice the charge, but I have half the distance. Okay, so since I have twice the charge and half the distance, that's a 2 over a quarter, that's 8 times the force. So here, my force is equal to 8 times 16. That's what, 80 plus 48, 128 newtons. So that means, well, I can probably almost guess that the answer is E. It definitely can't be these two. Because if I think about my vectors, I have one small vector and one really big vector. That means that my force vector is going to be down and in that direction. Remember, this vector, I drew it not relatively correct. This vector is actually going to be really big, right? It's 128 newtons. And then I can solve for this angle. But let's go ahead and just figure that out. So this is 16, this is 128. Theta then is the inverse tan of 128 over 16. It's 83 degrees. Okay, so E is the right answer. Units for the electric field are that, or it could have been also this, but that wasn't an option. Oops, sorry. Oh, did I have an extra page in there? Oh yeah, I'm sorry. Okay, so I have an extra page. Well, I'll take that out. Electronegativity is based on the principle that the closer an electron is to the atomic nucleus, which I'll read that. But what this has to do with is what happens when the radius decreases by half to the force. Well, we know that force is proportional to 1 over r squared. So if that decreases by half, this is quadrupled. We saw that previously. This, by the way, was an MCAT practice problem. It had a bigger passage preceding it, but I just extracted this piece. Remember, with the MCAT, you have these reading sections where you really need to be able to interpret and understand what's going on. And then you also need to know a little physics as well. So it's really about reading comprehension, but you need to know the physics too. So this configuration of charges, if Q1 has a magnitude of 3 coulombs, this is 3 coulombs, and notice that it is positive because the field lines are coming out. What is the magnitude of Q3? Look, I made this really easy for you because I have 3 field lines coming out of that 3 coulomb charge, so each field line will represent then a 1 coulomb of charge. So 1, 2, 3, 4, 5. So I have 5 coulombs, and they are coming out, so it should be positive. By the way, if I wanted to know this one, out of 1, 2, 3, 4, 5, 6, it would be negative 6 coulombs. Consider configuration of charges. What point is the electric field equal to 0? Let's just pick some places. So over here, the electric field due to that one is really big because it's attractive to that, and to the minus 2q it's also attractive. So it's not that, it's never going to be that. So it can't be A. Similarly, over here, electric field can't be that, so it's not going to be that. It's either B, C, or D. And remember, in general, probably going to want to get farther away from that big charge. I know that if I try to go to C, I'm going to feel a big electric field due to that one, and a smaller due to that one, so it can't be C. I'm betting that it's D because I'm far away from that. So I feel an electric field due to the minus 2q, and I would feel a bigger electric field due to the minus 4q, but I'm farther away from it. So D is the right answer. Two charges are arranged in this figure. Where is the electric field of these 2 charges equal to 0? This is probably the most challenging problem on the whole test. Let's look at it. So First of all, if I look at all the different places, I know that my point is going to have to be over here. Let me show you why. It's going to feel, if I call this Q1 and this one Q2, E1 is going to be in this direction. That's E1. And E2 is in that direction. It's smaller, or it can be the same size, even though Q2 is 3 times the size of Q1 because it's farther away. So I know it has to be over here. So let's see what that gets me. That gets me rid of this one, and this one. So now it's really just a matter of choosing between these two answers. Let me show you the mathematical way to do this. I think this is probably the harder way. The harder way is to say that E1 is equal to E2, and then define this as X. So E1 is KQ1 over X squared, and E2 is KQ2 over X plus 2 squared. And the K's cancel. The nanos can't, or no, these aren't nanos, so I'll just leave that in. So I have Q1 is 1 coulomb over X squared. I'll leave the units off here. And Q2 is equal to 9 over X plus 2 squared. So I get, solving this, I get 9x squared equals X plus 2 squared. I can square root both sides. Fortunately, I made the numbers nice and easy for you. So I get 2x equals 2, so x equals 1 meter. All right, so the answer will be B. But, given that, let's think about this. I have a charge that is 9 times the size of the other charge, kq over r squared. If I have a charge that's 9 times, and I want the electric field to be the same, then that means the distance has to be 3 times the distance. So that means that this distance has to be 3 times this distance. So if this is 1 meter, or excuse me, if this is, so I can go in and look at these numbers and pick between 1 and 3 and find that, oh, if this is 1 meter, that means this is 3 meters. So that distance is, the 3 meters is 3 times 1 meter. Or if I try the 3 meter, I put in the 3 meter here, that means that this would be 5 meters. See, that doesn't fit that requirement that the distance is 3 times the other distance. So I think that's probably the easier way to think about it, that B then is the right answer, or you can do it this mathematical way. We did have a similar problem to this on some past exam where you had to do a similar approach. All right. Electric field is most directly related to that. Here I have this neutral conductor. I'm going to get the electrons moved down here, and that will leave positive charges here. So the correct answer then would be this one. Remember that protons are actually stationary. It's just I get this extra electrons down here. Negatively charged object has that only. Let's see, this was actually from a past exam. Brought near to a neutral conductor, and so I get negatives over here, leaving a net positive charge over here, so B is the right answer. Electrical insulator is B. Okay, where will it move to? If a proton is at C, where will it move to? So remember, protons tend to move from high to low. They'll tend to move in that direction. So here I'm at about 8 volts. I want to move lower. That means I'm going to move towards D. Okay, I'm looking at potential energy. Potential energy, remember, is KQQ over R. What must Q do? I move these charges so that they're 3 times as far away. But I want to keep the same potential energy. In order to do that, I have to increase that by 3. So this was 1 coulomb. Now it needs to be 3 coulombs. Find that for the potential here to be 0, what must Q1 be? Well, I can calculate it here. V2 is equal to 9 times 10 to the 9th. 9 times 10 to the minus 9 divided by the distance, which is 3, so that goes 3. So this is 27 volts. Now, in order for it to be 0, I know that this charge has to be negative, so I can get rid of those two rather, and then I want to say that negative 27, that's what the voltage due to V1 must be, is going to be equal to 9 times 10 to the ninth Q divided by 5. So, yeah, because this distance is 5 meters. I'm going to go ahead and get rid of this 9 and say that this is in nanocoulombs, right? Because I have that nano in there. So I'll just get rid of that 9. And then I'll solve that for Q. And I find that Q is equal to 15. So A is the right answer. Oh gosh, this is a lot like the previous one. If I release a proton at point A, they tend to move from high to low, so it'll go to the left. And then here, which of these show a potential equal to 0? Remember, you're looking for where the distances to opposite charges are the same, and so that doesn't work for me. Let's see, does it work here? It does work here, I think. Yeah. So it looks like B is the right answer, because those are all equal distances to opposite charges. So B is the right answer, and then electric potential is A. All right. Tough exam. It's probably the toughest. It is the toughest exam of the semester. Exam 2 will be similar. And frankly, I think it's, I know you're not all going to think this, but I think it's probably the toughest exam of the entire year. Okay, good job.